Hi guys, today we'll be doing vector dot and cross product. I'll be first going to the dot product and some concepts related to the dot product, and then I'll be visiting the cross product and some concepts related to the cross product. Today we will want to be doing proving of some theories. The examples, if you guys want, you can mention them in the comments. Then I will have a separate video regarding the examples. Okay, let's go with the dot product first. The dot product, if you have two vectors, let's say vector A1, 2, yeah, and then we have another vector, this is vector B, okay, sorry for the caps. Okay, the dot product between vector A and vector B will be A1 multiplied by B1 plus A2 multiplied by B2 plus A3 multiplied by B3. Okay, so this is the dot product formula. Now, if you can notice this, the dot product is possible for vectors with two dimensions, and it will always give you a scalar product. Okay, the dot product will always give you a scalar value. As you can see, there is no direction involved here. It will always be a scalar value. Now let's consider this formula, and let us consider a triangle. Let's say this is a triangle. It's not a right angle triangle, just a normal triangle. I'll put the directions for the triangle. These are directions. So if this is vector B and this is vector A, so this vector automatically, if you know from the law of addition of vectors in triangles, you know that it is negative B plus positive vector A from tail to head. So it will be, you can write this as A minus B. Yeah. What if this angle was theta? Yeah. So now let's find out what is the value of this vector. What is the length of this vector? Okay. Now the length of this vector, actually our main goal is to find out another formula for the dot product of A and B. But for this we need this triangle to prove that. So according to the law, cosine law, we know that square is equal to A square, magnitude of A square multiply the magnitude of vector B square. Sorry, here I got this wrong. So plus the magnitude of the vector B square minus 2 into the magnitude of the vector A into the magnitude of the vector B into cosine of the angle between them, which is in this case theta. This law is very famous in trigonometry. It's called the cosine law of triangles. It is also available in many high school textbooks of maths. By the way, just putting out a point there, all my materials are taken from a textbook called Calculus Early Transcendentals with 7th edition. Okay, let's get back to our content, okay? So this side, it can be written as, I'll write this as A minus B into A minus b. Okay, right there. Okay, and let's go ahead and write down the right hand side as it is. Okay, now let's expand this to the magnitude of A. Okay, magnitude of A squared minus 2 into magnitude of A into magnitude of B plus magnitude of B squared is equal to the right hand side completely again. Okay. Okay, now how did I get this? This is a simple formula from a minus b whole square, where the formula will give you a square minus 2ab plus b squared. Yeah, this is a formula you can learn from the algebra. Again, it's from high school, it's just basic maths. So from this equation, we can cancel out a square and a square. We can cancel out b square and b square from both the sides. Now we are left with minus 2. Let's move it there. So I'll not write it here because I think it will be difficult to see. So I will continue up here. I will remove this part. I'll remove this part, and we can see that it will be minus 2 into A, magnitude of A into magnitude of B is equal to minus 2 into A, magnitude of A into magnitude of B cos of the angle between them, which is theta. Minus 2 and minus 2 can get cancelled. This, in other words, is the magnitude of the dot product is equal to magnitude of A into magnitude of B into cos of theta. So this is the one formula for the dot product, and then the other formula was mentioned just a few minutes ago in the video. Yeah. So keeping these two formulas in our mind, let's go on and deal with something which is called the direction angles. So suppose we have the coordinates right there. We have this coordinate system right here. This will be the z-axis, this will be the y-axis, and this will be the x-axis. This is the origin. This is a three-dimensional coordinate system. Let's take a vector. This vector is A. Yeah, and let me write down the value, the vector A in terms of its components. A1, A2, A3. Okay, so now the vector A is making certain angles with each of the axes. Yeah, it's making certain angles with each of the axes. Let's say the angle it's making with the x-axis is known as alpha. The angle it's making with the y-axis is known as beta. And the angle it's making with the z-axis is known as gamma. Okay, so now we know that what is a dot product formula. The dot product formula says that dot product of now vector A with B is the magnitude of A into the magnitude of B into the cosine of the angle between them. Now let's make the cosine of the angle between them. The cosine of the angle between the subject of the formula will be over if you just take the magnitude of A on the other side and the magnitude of B on the other side, you will get the cosine of the angle between A and the other vector as the subject of the formula. Okay, now let's take the cosine, the angle as alpha. Let's replace theta with alpha. So if theta is with alpha, A will be, let's replace A there on the numerator. We have A1, A2, A3 dot. So what is the other vector B? In this case, B will be the x-axis. And the x-axis has this vector, 1, 0, 0, because the other axes are 0 because it's parallel along the x-axis. The y-axis and the z-axis will be 0. And we can hear the magnitude of A will remain as it is into the magnitude of this vector, which will be 1 squared plus 0 squared plus 0 squared. So cosine of alpha will be if you see the dot product, it will be A1 into 1 plus A2 into 0 plus A3 into 0. So it will be only A1 left on the top over this whole term will become 1 if you can check using your calculators. So the denominator will be left with the magnitude of the vector A. So this is called a direction angle. Okay, so similarly we get 3 other direction angles. The other direction angles are, the 3 direction angles can be given by cos alpha is equal to A1 over magnitude of A, cos beta is given by A2 over magnitude of A, and cos gamma is given by A3 over magnitude of A, and you know the vector A can be given by A1, A2, A3. Okay, these are called the direction angle. Suppose we have a vector A. I'll give the same values, A1, A2, A3. We have a vector B. And then we have another vector C. Now, this vector C is special. Vector C, vector A is perpendicular to vector C, and vector B is also perpendicular to vector C. So we can say that vector C is the cross product of vector A and vector B. So now we need to derive a formula for vector C. And the cross product will always give you a vector product. It will not give you a scalar, it will always give you a vector. So let's go ahead and do the derivation. So first of all, if vector A and C are 90 degrees to each other, their dot product will be 0. Let's see how is that possible. Will be cos of 90, right? The cos of 90 will make it 0, so vector A dot vector C will be 0. The same thing goes for vector B dot product with vector C. We'll have zero. So the dot product of any two vectors that are perpendicular to each other will always be 0. Now I'll remove this information here. We'll use this information, these two lines, to get our expression for vector C. So let's remove these. So we will have the dot product of vector A and vector C according to the formula will be A1 dot C1 plus A2 dot C2 plus A3 dot C3 is 0. Okay, let's name this equation 1. Equation 2, the dot product of vector B with vector C will be B1 dot C1 plus B2 dot C2 plus B3 dot C3 is 0. Now let's do something. Equation 1 multiplied by B3 will give us A1 B3 C1 plus A2 B2 C2, A2 B3 C2 plus A3 B3 C3 is equal to 0. Equation 2 we will multiply by A3. When we multiply equation 2 with A3, we will get A3 B1 C1 plus A3 B2 C2 plus A3 B3 C3 is equal to 0. So let's name this equation as equation 3 and let's name this as equation 4. I'm going to remove the top part. Okay, I'll remove this part. I'll remove these parts also. So now equation 3 minus equation 4, let's write this. Let's subtract equation 4 from equation 3 will give us A1 B3 C1 minus A3 B1 C1 plus A2 B3 C2 minus A3 B2 C2. These two terms, when you subtract them, they're similar terms, they'll become 0, and this whole thing will become equal to 0. So let's remove these as a whole. Now let's make C1 common. C1 as a common is A1 B3 minus A3 B1 plus C2 common, and then we'll have A2 B3 minus A3 B2 will become 0. So now here is a complicated situation. I would not say complicated, but an unusual situation where we have this situation right here, similar to this. PC1 plus QC2 is equal to 0. In this case, C1, if you notice, if C1 is equal to Q and C2 should be equal to negative P. Okay, so C2 is equal to negative P. So let's do that. If C1 is Q, C2 is a negative P. So let's put PQ minus PQ. So let's do that. So C1 will be, in this case, our Q is this one right there. So A2 B3 minus A3 B2. And our C2 will be negative P, so it will be A3 B1 minus A1 B3 right there. Okay, so let's remove this all from here. From our equation 1, if we substitute, our equation 1 was actually A1 C1 plus A2 C2 plus A3 C3 is equal to 0. We'll substitute the values of C1 and C2 there, so we will get A1 A2 B3 minus A1 A3 B2, then plus we'll have A2 here, so A2 into C2, we have A2 A3 B1 plus, sorry, negative of A2 into A2 A1 B3 plus A3 C3 is equal to 0. So what I just did, I took equation number 1 and I substituted the values of C1 and C2 in the equation number 1. Now let's look for something. If you notice very closely, A1, this term right there, and this term, they're exactly the same. A1, A2, B3, A1, A2, B3, so we can cancel them out. We are left with negative A1, A3, B2 plus A2, A3, B1 plus A3, C3 is equal to 0. Okay, now as we can see, we can multiply the entire equation by 1 upon A3. That will leave us with negative A1 B2 plus A2 B1 plus C3 is equal to 0. So C3 can be written as here A1 B2 minus A2 B1. Let's see, this is the correct one. Minus A2 into B1. Yes, exactly. This is the correct equation for C3. Yeah. Now let's remove these things. Okay, and let's write what was C1, what was C2, what was C3. The vector C can also be determinant can also be determined, using this determinant of 3 by 3 matrix. It will be A1, A2, A3, B1, B2, B3, which will give us the same thing it's here, but I'll just write. We'll have I, and we'll cover I. We'll have A2, A3, B2, B3 minus J, and then when we cover the column and row of J, we will have A1, A3, and then we'll have B1, B1 and B3. Okay. B1 right there. And then we'll have the last term, but not the least. We'll have here K, the K terms. We'll cover the column and row of K. It will be A1, A2, B1, B2. Okay. So now let's move on to let's see how we can apply the cross product in many geometric forms, in many geometric shapes, okay? So let's take a parallelogram. A parallelogram. You know, a parallelogram has all the sides that are parallel to each other. Okay, all of them are parallel to each other. They're parallel, the opposite sides are parallel and equal to each other. So this is the vector B. This is the vector A. Okay. This is the angle theta, the angle between the vector A and vector B. So, this particular, the height, okay, this is given by the magnitude of B into sine theta. From the trigonometry, we can know this. So the area of the parallelogram, as we all know, is length into height. So area will be, length is the magnitude of the vector A into the magnitude of vector B sine theta. So that's the height. And area can be written as the magnitude of the cross product of vector A and vector B. Okay. So here we get the C1, C2, and C3 values. Okay. So now let's go and write C3 in its C in the vector form. So we have the vector C, which is equal to the cross product of A into B, is equal to C1, which is A2, B3, minus A3, B2, and then we have A3, B1, minus A1, B3, and then comma, we have A1, B2, minus A2, B1. This is the vector C. Okay, keeping this in mind, let's go ahead and compute. Let's go ahead and compute the magnitude of the cross product of A into B. As we know, with all the vectors, the magnitude will be, you take the square root of the square, the sum of squares of all the components. Square root of sum of the squares of all the components, so it will be A2, B3. So minus A3, b2 whole square plus a3 b1 minus a1 b3 whole square. Then we'll have the last component. We'll have a1 b2 minus a2 b1 whole square. And then finally the square root of all the sum of squares of all the components. Yeah? So now let's check if we have the correct. We have a2 b3 minus a3 b2, a3 b1 minus a1 b3, and then we have a1 b2 minus a2 b1. What we will do, we'll shift the square on this side. We'll take square on both the sides. So when we take square on both the sides, square and square root will get cancelled. Will be left on the left hand side as the magnitude of a cross b whole square is equal to, let's expand these. When we expand these using a minus b whole square formula, we will get a2 square b3 square minus 2 a2 a3 b2 b3 plus a3 square b3 b2 square, a3 square and b2 square. For this term it will be a3 square b1 square minus 2 a1 a3 b1 b3, and then we will have plus a1 square b3 square. Then the last term is remaining same. We will use a minus b whole square formula. We will have a1 square b2 square minus 2 a1 a2 b1 b2 plus a2 square b1 square. Yes, so now we have this expression. Yeah, so now let's write expressions which are similar to this thing in one side, and expressions which are similar to this term on the same side but separately. Yeah, so I can rewrite this as so I'll write only the a1 square terms first. a1 square b3 square. I'll put a small tick mark so I don't lose track. There are a lot of terms. Plus a1 square b2 square. Okay. Then I'll write the a2 square terms. Where are the a2 square terms? We have one right there. Was a2 square and then b1 square. Plus, let's see if you have any other one. Yes, we have one right there. Plus a2 square b3 square. Then let's do the a3 terms. We have one right here. We have one right here, which is the here a3 square b1 square, and then we have one right there. We have a3 square and then b2 square. Yeah. Now let's write terms similar to these next to them. We will have 2 a2 a3 b2 b3 negative 2 a1 A3 B1 B3 negative here to A1 A2 B1 B2. Okay, now let's I'll remove the top part so we can continue. Continue from the top. Okay. So let me just write. So in this step, what I'll particularly do is I'll introduce some missing terms. Like not missing terms, I would say, but I'll introduce some new terms, but I will add the new term and subtract the new term at the same time so the equation does not change. So my first term that I'll introduce is A1 square B1 square. So that we can keep track that this is a new term, I will box it in blue, and then let's keep going. Plus A1 square B2 square plus A1 square B3 square. Okay, now let's introduce another new term. Let's introduce A2 square B3 square. Sorry, A2 square B2 square. Let's introduce, sorry, I'll write this here. Plus A2 square B2 square. And I will again highlight it in blue so it reminds me that I need to subtract these terms so that the equation remains unchanged. A2 square B2 square plus A2 square B1 square plus A2 square B3 square. Then I'll have here, I'll introduce, not now, let's introduce it later, A3 square B1 square plus A3 square B2 square. Yeah. And another term I will introduce is plus A3 square B3 square. When I introduce this term, it will become, I'll highlight it in blue. So whatever terms I've highlighted, these are the new terms I've introduced. So let me just subtract them so that I don't change the equation. Always remember, whatever you do when you're proving something, you can add, you can subtract terms, but you can never change them. So if you add them, you need to subtract them at the same time. If you multiply them, you need to divide them at the same time. Minus A3 square B3 square. Let me just underline them, telling it will show that they have been subtracted to make the equation, to keep the equation, what do you say, unchanged. And the remaining part of the equation can be written as, minus 2 A2 A3 B2 B3 minus 2 A1 A3 B1 B3, and then minus 2 A1 A2 B1 B2. Yes, so now let me remove this part and we can go ahead. So what was the benefit? The benefit was, if you notice, till here, from here till here, it is nothing, sorry, from here till this part. From here till here. if you notice, this is nothing but a1 square plus a2 square plus a3 square into b1 square plus b2 square plus b3 square, and the remaining part is actually here, a1 b1 plus a2 b2 plus a3 b3 whole square. So how it's a squared plus b, a plus b plus c whole square will actually give you a squared plus b squared plus c squared minus, so it will give you minus, it should give you minus 2ab, minus 2ac, minus 2ac, and minus 2bc. So this is actually, this will be the, this is our bc, this is our AC, and this is our CA. Sorry, this is our AB. Okay, so a square, a plus b plus c whole square will actually give you this formula. How I have just reversed that formula back, and so these two are pretty interesting formulas here and there. We can write this as, the interesting thing about this is actually the magnitude of a square into the magnitude of b square, okay, minus, this is the dot product. So the dot product can be, this is actually the dot product square. So the dot product square can be written as a into b cos square theta. Okay, so when we write this, I'll remove the top part. Okay, I have removed the top part. Okay, so now I can simplify this further. I can write is equal to, I'll take a magnitude of a whole square magnitude of b whole square common, and I'll be left with 1 minus cos squared theta. We all know what is 1 minus cos squared theta from trigonometry in high school. It is sine squared theta. It is sine squared theta. We will take square root on both the sides. We will get the cross product magnitude. If you want the magnitude of the cross product, it will be the magnitude of vector A into the magnitude of vector B into the sine of the angle between the vector A and vector B. So this is the vector form of the cross product. This is scalar form if you want the magnitude. A simplified version. This shape in particular is known as parallelepiped. Okay. Now, for this shape, the volume of this shape is a three-dimensional shape, will be area of the base into the height. Okay. Now the area of the base is very simple. The area of the base is given by the magnitude of the cross product of the vector B and vector C. Okay, the height. Now the height can be given by, this is the angle theta. Okay, sorry. Now, the angle theta is the angle that the vector A makes with the vector that is perpendicular to both vector B and vector C, hence the cross product of vector B and vector C. And the height will be given by h is equal to cos theta. Okay, we'll just put that together in the volume formula. Volume is equal to now, if you consider this one vector and this the second vector, we can write the volume as we can write the volume in this form because we know that this is the formula for the dot product. So this is known as triple scalar product. This is known as the triple scalar product, and from the name it suggests that you'll never get a vector out of this, you'll only get a scalar. Guys, thank you for watching the video. If you have any questions that is particular to vector dot and cross product that you want me to do, please write them in the comment section. I will try my best to have a video out for some applications of vector dot and cross product in the engineering world, and I think then all these formulas will be made much more clear. But if you have any particular questions, please post them in the comment section. Thank you and have a nice day.